Yeah, is it visible?
Yes, madam.
Okay, thank you. So, my topic for today is the VLSI architectures for deep learning. Both the areas are most happening fields in the area of research and in the practical implementation of many real world applications. Deep learning today has become a buzzword, particularly for applications like object recognition, pattern recognition, uh, any detection and recognition tasks. Deep learning has become the other word, the alternative word, or a synonym for all these recognition tasks. And the simulations of deep learning can be done on any kinds of simulation environment. But because deep learning is more into the practical applications, is into the real world applications, hardware implementation or implementation of deep learning on a processor has become a most significant problem in the world of research. So uh, the, the scientists or the researchers are working towards designing a processor that is suitable for implementing the deep learning algorithms. So why is it so significant to develop a processor for implementing deep learning algorithms is what uh, I'm going to deal in the coming half an hour or 45 minutes or 1 hour time the organizers are going to give me. So it's like we all know, coming from the VLSI background, I hope most of the people in this participants, I think they are all interested in VLSI. So anybody who is interested in VLSI are well known, they know well about the Moore's law and its strength, wherein during 1940s, the number of floating point operations per second were 1000, but now we are in the era where the number of floating point of operations per second are in the order of 10 to the power of 15 pico floating point operations per second. So the processors they started from implementation of scalar, superscalar, vector, and parallel algorithms. Now in the era wherein we require just not a parallel processing architecture processor, but a graphical processor unit. So only a graphical processor unit can be so fast to implement the at least one pico floating point operations per second. So we are in that era. So we started with we started implementation of our algorithms on CPUs with quad cores, and we thought it is like I mean the fastest thing that we had. We had four cores, but now it's just not a four core. We had almost 5,000 cores in one GPU. So that is the era in which we are living. So which results in massive parallelism. So the memory hierarchy that these kind of architectures, these kind of processors are following is called a Kepler memory hierarchy, in which a thread is shared among shared memory and the read-only data cache, along with L1 and L2 caches, which interface with the dynamic RAM. So this is the era in which we are, in which the memory plays the number of processors, the massive parallelism, it plays a major and significant role in implementation of algorithms. So, if you see that the Moore's law has enabled us to go down. See, in the previous slide itself, we have seen an L1 cache memory, an L2 cache memory, and a read-only data cache, along with a shared memory. So, these kind of memory, this kind of deep memory hierarchy is being enabled by means of the Moore's law. And the number of pipelines, just they're just not one or two stage pipelines. We have now almost closer to 10 to 20 stages of pipelining, taking multi-threading and multi-processing. So this is the era in which we are living now. So the all these significant contributions have led for need for an improvement in the number of operations per instruction. Yeah, by 100x, by 100 times. If you want to know more about the importance of this 100x improvement in the operations per instruction, and which requires this many number of operations per instruction is possible through domain specific architectures. The best lecture I have gone through in this domain specific architectures is by Hennessy and Peterson. So they have given this lecture in April 17, 2018, with the title of the presentation being a new golden age for computer architecture. It's available in YouTube also. So they have given a wonderful. It's an interview followed by their. I don't say lecture. It's a sharing of experience, their experiences in the requirement of domain-specific architectures for implementation of the deep learning architectures, because because these deep learning architectures require large memory operations, very high computational complexity. So a normal SX or FPGAs, these kinds of architectures are not suitable for implementation of these architectures. So the real need for this the need for improvement of the processes better than 100x times better than the ASICs and FPGAs is wonderfully dealt in the lecture by Hennessy and Patterson with the title A New Golden Age. I request all the participants to go through this to understand how the computer architecture is evolving, more evolving from a CPU to a GPU. How massive parallelism is introduced into the processors. So now coming to our lecture, the actual topic of interest, that is the deep learning. So machine learning or deep learning, they are like deep learning is a part of machine learning. So and the data set size is limited. You have limited number of samples in a data set. Like you have only 1,000 samples in a data set or 5,000 samples in a data set. Then it's like it is always preferred to use a machine learning for classification or recognition, or NLP or robotics based tasks. But the data size is huge. The volume is huge. Like you have millions of samples in a data size in a data set. Machine learning algorithms will not be are not suitable for implementation of pattern recognition and the classification tasks for such huge volumes of data. In such situations, we go for deeper architectures with deeper layers. We go for deep learning. So fundamentally, deep learning is a subset of machine learning. So, whatever the machine learning or deep learning, they are very much useful on images. Like you go on a traffic, and you need an autonomous vehicle. An autonomous car is going on the road, and it has to understand the scene, the road on which it is traveling. It has to identify the type of vehicle, the human being, the animals, the traffic signals, the posts, the trees, and so on and so forth, the infinite number of objects that it comes across on the scene, that is the traffic, and it has to find a path to go in an obstacle-free path from a given source to a destination, in which it is doing multiple tasks of identifying the scene, understanding the objects, and finding a path. So all these different tasks that I have divided a big task of autonomous navigation into three subtasks of identifying the scene, finding a path, and avoiding the obstacles. This is one wonderful examples of machine learning, and it is also used in. It is very much useful in healthcare domain in identification of many diseases, and it is useful. Now we are commanding Siri to perform so many tasks. If you are an iPhone user, Siri, you show me, you go take me to this website. Siri, you do this. Siri, you do that. And if you are all Alexa users, we ask Alexa to switch on the lights. And if you are a Google TV user, you ask the Google Assistant to switch on your TV, to switch on your smart appliances. So and then nowadays anybody can talk in any language, and in a public concert you can just translate them using the translator live. So any language can be translated to any language, and so you can just convert your speech into text and text into speech, or like pick and place robotics and reasoning, how like prediction of many things. So all these kinds of tasks are now automated only because of the advent of the wonderful concept called machine learning, which is a subset of artificial intelligence. So artificial intelligence is nothing but human intelligence, is mimicking or aping of human intelligence. God made, or any superpower has made a wonderful creature called human being, who has a lot of wonderful intelligence. Even a 3-year-old kid knows how to step down without falling down the steps, and even they know what to touch and what not to touch. After 2 years of exploring many things, they understand what to touch and what not to touch, what to eat and what not to eat. So even a 3-year-old kid has a lot of intelligence. So the intelligence that any biological a mammal, any dog, any human being, any living creature is possessing is a natural intelligence. So imparting this intelligence to a computer by means of algorithms and mathematical equations is nothing but artificial intelligence, making the machine perform tasks which a human being can do with their natural intelligence is artificial intelligence. So the training that is imparted to the machine to understand the tasks, to do certain tasks, is called machine learning, which is a part of artificial intelligence. So, as I told you earlier, deep learning is again a subset of machine learning, which is having multiple layers uh, to to do processing at multiple levels. Is deep learning. Whatever artificial intelligence, machine learning, deep learning are fundamentally, uh, I mean, like have grown from the foundation of statistics. So, statistics is the foundation for all the algorithms that we develop, that we implement in this machine learning and deep learning. And alongside the statistics, the most important concepts from mathematics include the optimization techniques and linear algebra. So linear algebra, statistics and optimization techniques form the foundation for implementation of any artificial intelligence or machine learning or deep learning algorithms, which in turn are useful in performing big data processing, implementation of sophisticated algorithms for performing any real-time application, and they are also, but they require high performance machines. Should I stop? Any problem?
Hello.
4J3 Hitesh, I think he has to mute himself.
Hello, 4G3 Hitesh. Mute yourself. Okay, madam.
Right. So, however, these sophisticated algorithms can be implemented only on the high performance machines. So now, first, before we understand the VLSI architectures for the implementation of deep neural networks, let us walk through the fundamentals of deep neural networks and have a little understanding of what is a deep neural network, starting from a neuron. So the neurons are the fundamental parts of our human brain. So any human brain has 10 to the power of 5 number of neurons. So these neurons are interconnected to the neuron, the important parts of the neuron. The first one, so the first one is called the nucleus. So this is a cell nucleus, and it has this is called the axon, through which electrical impulses are given to the other neurons through to which it is connected, and it also has the other parts called dendrites, which acts as sensors to receive signals. So the dendrite, the cell center or called the soma, and the axon are the important parts of a neuron. So these the electrical impulses here are connected to other parts of the neuron. So the neuron that is sending the signal to is called a transmitter or a neurotransmitter, and the neuron that is receiving the signal from others, first transmitter neuron, is called a receptor neuron. So every transmitter neuron has, or a receptor neuron receives the information through what is called synapses. Synapse is a connection. Whenever some information is received, a synapse is formed. It is like, how do we understand in a normal layperson language? This is we are engineers, and I spoke a lot of biology. So what happens? How we understand things? So it's like uh, let me take today's example. Many of you have seen me for the first time. So now, if I close, so whenever you have seen me now for the first time, what happens is the visual cortex neurons. So the neurons which are responsible for seeing things are placed on a cortex called visual cortex. Our human brain is divided into number of cortices. Cortices is a sectors. Cortex is a sector. So we have audio cortex to understand audio signals. We have visual cortex to see something, and not only just to see, but to understand what we see. Is done by means of a visual cortex, and we also have cerebral cortex performing the locomotive task. That means I'm moving my hands, I am moving my head. All these movement tasks, the physical tasks, movement related tasks are performed by the cerebral cortex. Chinna medadu antam kada, are performed by the cerebral cortex. So like that, the human brain has several cortices, and each cortex has several neurons to perform all the auditory tasks. That means speech and hearing, and the visual tasks like seeing and understanding, and speaking. All these things are each part of the human brain performs certain tasks only because of the presence of the biological neurons. So what happens is, whenever you have seen me, you already have 10 to the power of 5 neurons. So among this 10 to the power of 5 neurons, few neurons are situated on your visual cortex. So whenever you are seeing something for the first time, the visual neurons will get excited. So they get excited, and they send whatever features you see about me. How am I looking? How are my facial features? So my facial features, each of my facial features, they are given a connection. So, and then how I speak. So on my voice is given another connection. It excites certain other neurons in the auditory cortex. Now, like that, this is the first impression that happens. That is what happens when you're seeing me for the first time. Now, what happened? I switch off my video camera and I keep on talking. Though I'm not visible for you, you can just your brain can visualize me, at least vaguely, if not with not so much clarity because you have seen me only once. Uh, you can visualize my face, uh, how I look, how I talk, like that. And let us say my audio is lost. So if I talk to you, to any one of you through a mobile phone, you can recognize at least vaguely that she is the person who talked to us, who has given a lecture today for us. So, how is it possible? This is possible because of the synapses, the connections that are formed between the transmitter and receptors different neurons of our brain. Okay, and these neurons are responsible for all the understandings that we have. So uh, it now we'll speak as an engineer. Now I see this neuron as completely a black box. So the inputs for this neurons are coming from dendrites. The processing is done by the center of cell center or soma of the neuron, and the output is coming from the axon and is given to the synapse of the next neuron. So this is how we see the black box. So this complete cell center is denoted by this black box neuron, and the information that is received by several dendrites here is called input, and whatever electrical impulse that this neuron is giving is called the output. Okay, so this is about how a biological neuron works in the human brain. And all these neurons are arranged in the form of layers, number of inputs followed by number of processing layers followed by number of output layers. So inspired by the biological architecture of or the biological arrangement of the biological neurons in the human brain, the researchers have developed an artificial neural network. So, in the artificial neural network also, you will have several layers. One belonging to the input layer, second layer belonging to processing layer, and third layer belonging to output layer. The more the number of processing layers, the neural network transforms itself from a machine learning neural network or an artificial neural network to a deep neural network. So this is the fundamental thing that we need to know before we understand about the VLSI architectures for deep learning. So as I told you, so this is how the brain has number of layers for processing. So as I told you, these are the input layers. This is one neuron, this is one neuron, this is one neuron. This is one dendrite are all inputs. These are all processing units, neuron, and outputs are also coming from the axon of that particular neuron. The more the number of hidden layers, here you have only input is not counted as a layer, hidden layer is there and the output layer is there. So you have the number of hidden layers will give you the complexity of the architecture. If you have only one hidden layer, it is called a one single layer neural network. If you have two hidden layers, it is called a two layer neural network. If you have more than three number of hidden layers, then only we call it a deep neural network. So the main purpose of this neuron is to compute an activation function, so which we will discuss later. So and these neurons are arranged in layers. So now, so these are all MLP 0 is nothing but multi-layer perceptron 1, long short-term memory convolution neural network. So if you take an MLP 0, it has 5 layers. Whenever it has 5 layers, it is definitely a deep neural network because the number of layers are more than 3. So in a 5-layer deep neural network, we will have 20 million weights and 200 operations per weight. So the total number of operations are 20 into 200. So that is around 4,000 million operations per weight for a 5-layer neural network. So see the computational complexity. For LSTM0, you have 58 deep neural network layers, that is 58 hidden layers, and 52 million weights totally distributed around these 58 layers, and the number of operations per weight is 64. So 52 million into 64 is the total number of operations. So this is the computational complexity of each of these deep neural networks. So this is what makes it complex to develop a VLSI architecture for deep neural network. Implementation using an FPGA or implementation using an ASIC almost becomes impossible to implement so many number of complex operations, which include arithmetic and logical operations. So, most of the practitioners choose Instead of starting from a scratch to do a classification task or recognition task or to perform natural language processing tasks like speech to text conversion or speech recognition tasks or any other translation task. So instead of starting from scratch, it is always difficult to start from scratch. So what they do is uh, they choose, most of the researchers, they choose an existing system and they modify the existing system a little so that it meets their requirements. Such a kind of learning is called transfer learning. So most of the researchers who are working in deep neural network area will prefer to use transfer learning rather than starting from scratch, because it's already a proven algorithm, and if we can do a little modifications to our requirement, our accuracy and precision will be higher. And and uh, the the working of any deep neural network architecture is divided into two parts. One is training the architecture, and second one is testing the architecture. So, best example, when you are in a school, so we buy hard things, right? Like we want to learn a table two table. So what the teacher does, she trains us. Two ones are two, two twos are four, two threes are six. Like that, she repeats 3 times, 10 times. Two ones are two, two threes are six. Then what happens after she is satisfied? How she will be satisfied? She'll says two ones are. Then the students have to reply two sir. Then students have to reply four. Then she says two three sir. Then students have to reply six. So if she's satisfied that all the students are giving the correct reply to her questions, what she continues with the next batch of uh, the table, that is two fours are two fives are two six are, like that she keeps on training you until you learn the total table. So that is called training. And then she's also taking feedback if you're learning properly or not. That is called testing. So the implementation of any deep neural network architecture depends on two factors. One is a training and second one is a testing. So here the neural network, now the student is replaced by a neural network. So the neural network is getting trained itself by means of a continuous feedback. So that is called learning with the teacher. So that means we know the output, we know we will have a prior knowledge of the output, and the neural network learns how much it deviates from the expected output and keep on updating itself so that the actual output that is coming from the neural network is almost similar to the expected output. So generally, the type of learning that happens with this kind of neural networks follows a stochastic gradient descent. I'm not going into the technical details of stochastic gradient descent because I don't know how much time I have. Anyhow, I'll just tell. So stochastic gradient is you have an expected output and you have an actual output. So initially, the error will be maximum. So we keep on making training the neural network in such a way that the error minimizes. The error comes to a minimum point. So initially the difference between the actual output and the uh, final output is high, and through number of iterations, slowly the error drops down to zero. So this is obtained by taking a batch of differences into account and keep on decreasing the slope by taking a gradient, and this gradient is descending from a maximum value to a minimum value. That is the reason why this is called a stochastic gradient descent. So this is the most general. It's not always stochastic gradient descent. There are a number of other supervised learning algorithms also there, but the most popular one is stochastic gradient. We also have optimization algorithms called RMS prop and momentum and so on and so forth. But that is one of the algorithms that is used in training the deep neural network architecture. So now let us see what kind of hardware is used for what kind of data. So if you take a text problem, so it is like let us say uh, he sits on a mat is a sentence we have. He sits on a mat. So where he is a preposition, sits, sorry, he is a pronoun, sits is a verb, on is a preposition, a is an article, mat is a noun. So now this word prediction, whenever we give a sentence, so it should predict the what you call the parts of speech. That is one pause stacking we call it. And this word prediction is when we are typing something in Google. So when you write something after two words are typed, based on the history, based on the history of the user who is using the browser, it keeps on predicting the next word. So that is word prediction. So to do that word prediction, 100 billion words from Wikipedia are taken as a training set. And for word prediction, the deep neural network architecture that is used is two-layer skipgram DNN architecture, and it is implemented on NVIDIA Titan X graphical processor unit. And the training to train this architecture, the two-layer skipgram architecture for 100 billion words, it took around 6.2 hours. So that is just a simple text, a word prediction. When it comes to audio, uh, for a 2000 hour audio database, the training time is around 3.5 days. And for image classification, for a 22 layer CNN, training 1 million images will take around 3 weeks. And for activity recognition, the training time is 1 month. So this is the complexity in the deep neural network architecture. The hardware have to tackle a huge data. So the memory is the biggest thing, the biggest constraint that the processor is having, and the processing this complex data is also a challenge for all the hardware that is going to perform these tasks. So this is one of the challenging things for any deep neural network architecture. So let us understand what would be the basic building blocks that should be there in any VLSI architecture. So if you know what are the parameters and identify what are the processings, what are the processes that happens in determining the output, then we can determine the corresponding building block for that particular operation. So if you take a multi-layer perceptron, this each neuron is called a perceptron. So, so if you take a multi-layer perceptron, this is one layer and this is one layer. So how many number of neurons are there is one vector. And what is the size of this input vector? How many inputs are there? You have three, let us say you want to determine, you want to, like classify the numbers. So each is a image. Each image is a m by n matrix. And like that you have 10 digits. So the input layer size is 10 by 10, m by n by 10. So how many number of neurons? For each digit you require one input. So from 0 to 9 you require totally 10 neurons here. So the dimension I becomes 10. And what is the size of the each input vector? Each input vector, what is the size? And what is the number of weights? Every neuron should be connected to all the inputs. So how many number of neurons are there here in the hidden layer? All these I should be connected to all the input vectors. So the number of weights, so these number of arrows will always be equal to, then that means if you have, here you have three inputs, and here you have 1, 2, 3, 4 neurons. So that means the number of weights will be 3 into 4. That means 12 weights will be there here. And if you come here, there are 2 neurons here and 1, 2, 3, 4. So 4 into 2, 8 will be there. For 8 weights will be there for this layer. So that is how you have to determine the number of weights. And the number of operations will be 2 into the number of weights, 2 times the number of weights. So the operations per weight is equal to 2 for a simple multi-layer neural network. So, so if you take here, so this is the vector matrix multiply. You have number of inputs. So this is a hidden layer. So here this hidden layer is determined by a vector matrix multiply, which has to be, which does the vector input is a vector, weight is a matrix. You see here input is a vector, I minus 1 by 1 vector, and you can see these weights are 1 to 2 dimensions. So this is a matrix. So here you have to perform multiplication between a vector and a matrix. So the first operation that is performed is for every layer, the first operations that is to be performed is a vector matrix multiplier, a digital system which performs vector and matrix multiplication. Then the neuron computes the weighted sum of all these things, and it will apply a non-linear activation function. So the next one, the next processing unit is the non-linear activation function, which should be stored in a register. So here you should have a subsystem, a digital system, to store the input vectors, a register, and to store the output you require a register. To store this, you need a two-dimensional array to store the weights, and you need a vector matrix multiply unit, and you require a non-linear functioning unit. So this block diagram is now visualized as a digital system consisting of these subsystems. So this is how we visualize the VLSI architecture for a simple multi-layer perceptron. Now the same thing, let us move and see how you can extend it to a convolutional neural network. So multi-layer neural perceptron is not a deep neural network. It is a simple artificial neural network. It is having only one layer. So whenever the number of hidden layers are less than 3, it is just an artificial neural network, not a deep neural network. So convolution neural network is definitely a deep neural network in which the number of hidden layers are more than 3. So here, generally the convolution neural network is useful for computer vision tasks, for all the object recognition tasks and pattern classification tasks. The convolution neural networks is used. So let us think only that we want to recognize a cat and a dog, or we want to recognize a dog. So how does the number of layers are used to determine which part of the dog? So the total, you have a dog image. When the dog image is given to the neural network, the first hidden layer recognizes only the horizontal lines and the vertical lines, and the second layer identifies the corners. Third layer recognizes the shapes, like how is the shape of the legs, how is the shape of the lobes, how is the shape of the nose, how is the shape of the eyes, like that, certain regions. And then the fourth layer exactly identifies certain region of interest. Let us say the region of interest is the ears of the dog. And then the top layers recognize whether it belongs to a Pomerian, whether it belongs to what you call German Shepherd, like that. What is the layer of the breed of the dog is recognized by the higher levels of the convolution neural network. So here also, fundamentally, it will have and again whatever is the like neural network you are taking, the input is given across some input layers. So all the input layers are in the form of a vector, and all the weights are in the form of a matrix, and the processing unit is always a what you call a vector to matrix multiplier, and at each layer we use a non-linear function to get an output feature map. So this is how we visualize the convolution neural network architecture. So now let us see the in detail about the parameters that are there in any convolution neural network. So here you have this is the layer, the input feature maps. The input feature maps, the horizontal lines, the vertical lines, the, the regions of interest, that how is the shape of the ear, how is the shape of the legs. All these are all features. So all these features are this is called a feature vector or a feature map. So you will take all the input feature maps and you give it to a vector to matrix multiplier, multiply with the weights. So the vector matrix multiplier performs the vector matrix multiplication and give it to a nonlinear activation function to get the output layers. So this is how we have the dimensions given for a convolution neural network. See how the complexity is being increased from a multi-layer perceptron to a convolution neural network, where the number of neurons are now number of feature maps I into dimensions of feature map in I whole square, and the number of weights per output feature map is now given from number of feature maps into dimensions of the stencil. Stencil is nothing but the kernel that we are taking. So this is the stencil, a 3 by 3 mask. We call it as a mask also. So this is a mask. So this is called a stencil. So dimensions of stencil, have you taken a 3 by 3 window, 5 by 5 window, 7 by 7? Generally take only what you call odd number, and sometimes we take a 32 by 32 size stencil or window also. So total number of weights per layer will be number of feature maps into number of weights per output feature map. Like that, the computational complexity, you see the total number of operations per layer have from 2 into weight dimensions to the total number of operations per layer have increased to number of feature maps to number of operations per output. So that is 2 into dimensions the of the input feature maps whole square into number of feature maps whole square into number of weights per output feature map. So this is how the computational complexity is increased from a simple multi-layer perceptron to a convolution neural network. So here, to reduce this many number of computations, what we do is, instead of considering each input, we just consider a batch of inputs across the input layer, and we reuse the weights once fetched from the memory across multiple inputs. So what happens? This increases the operational intensity, or it gives an ease in the number of operations. And we also perform quantization because see the image has gray. Each gray level is like, if you take a normal monochrome image also, you will be having 256 gray levels, 0 to 255 gray levels. So all those gray levels, we instead of taking 256 levels of quantization, we make use of either an 8-bit or 16-bit fixed point quantization. Okay, so in summary, when you want to perform any convolution neural network, we need a matrix vector multiplier, we need a matrix matrix multiplier, we need a kernel, that is the stencil is nothing but a kernel or a window or a mask, and then we need to implement the non-linear activation functions like a ReLU, rectified linear unit, a sigmoid unit, and a hyperbolic tangent unit. So these are the things that we have to implement to perform one layer of a convolution neural network. So these are the things that are required for the architecture for what you call the um, object recognition task, a computer vision based task. But the operations of a neural network are not limited to computer vision tasks. They are also used in speech recognition and language translation. For such things, we make use of neural networks called recurrent neural networks. So, for example, we want to translate the word sentence "now is the time" to Spanish, which should be translated into "momento es ahora." Then you require they require n number of layers for translation of this recurrent neural networks. So again, the architecture for this recurrent neural networks is, again, you should have output gate, a vector matrix multiplier, a nonlinear activation function, a concatenation function, an element wise multiplication function, an element wise addition function. So these are the number of things, and memory registers to store the short term weights, and long term memory output, short term memory output registers, and should have an input register. We should have registers to store the output gate weights and input gate weights and forget gate weights. So this is how an architecture, VLSI architecture for a recurrent neural network looks like. So these are so I told you the linear algebra also forms what you call one of the fundamental backbones for implementation of any machine learning or deep learning architectures. So the logistic regression is totally based on the sparse matrix and sparse vector multiplications. Dimensionality reduction is also based on sparse matrix and dense vector and multiple dense vectors. And deep learning is totally based on dense matrix vector and dense matrix matrix operations. So, like that, machine learning is mapped linear algebra. So, by seeing this, what we want to summarize is, definitely, whenever you are considering a processor to perform all these tasks, we should have a high performance and low power system to perform implementation of dense matrix operations, which include matrix to vector multiplications, matrix to matrix multiplications, and kernel-wise multiplications. So, like input vector multiplied will give you a result, or a matrix multiplied with another matrix should give you result. And we should have computing units to perform nonlinear functions like ReLU, sigmoid, tanh. So these are the requirements for developing any architecture for uh, the implementation of deep learning algorithms. Um, so now with this, I would like to explain about one case study about the VLSI implementation of a deep belief network using integral stochastic computing. So this is a deep belief network which consists of hidden nodes and visible nodes. So the hidden nodes are the computational nodes, and the visible nodes are the input nodes. So generally, these deep belief networks are useful for speech translation, or voice translation, audio translation, or any pattern recognition tasks. So how do we implement this architecture of a deep belief network using integral stochastic computation? Is the case study that we are taking. So, so this is a stochastic. We have a normal neuron. So the normal neuron is nothing but a perceptron which takes all the integral inputs, and it performs a vector to matrix multiplication and then gives an output. So instead of taking an integral inputs which is computationally complex, what we are doing is we are going to implement all these multiplication and addition operations using the OR gates and AND gates to reduce the number of computations. To do so, we are, instead of taking a normal neuron that we have seen till now, we want to implement a stochastic neuron. So the input for this stochastic neuron is just a 4-bit binary number or any integer number. So from that, we are going to have a stochastic bit stream generation, which is nothing but a comparator. So we take a random value of threshold 0.5, and we keep on comparing the bits for this bit stream generator, and we give according to it, we just give the probability of the output the probability that how many number of ones are there, how many number of zeros are there in that particular number. For example, in the number 0, 1, 1, 0, 1, 0, 1, 0, you have 4 ones out of 8 bits. So the probability will be 4 by 8. So now, now all these bit stream generated bit is given to a stochastic computing digital neuron, which consists of multipliers and OR gate and with the delay elements. So once all the computations are done by the stochastic bit neuron, again the real world is having a binary value. It is not having the stochastic value. So we use a counter to count the number of ones and zeros in this and give a binary converter. This is the basic underlying principle for generating a stochastic neuron. So, for doing the comparison to generate stochastic bit stream, we use linear feedback shift register to generate the pseudo random sequence, which is compared against a constant value, from which we get the stochastic bit stream. By making use of the stochastic computing, we perform the multiplication in stochastic computation is visualized as AND operation, and the addition is given by the addition is done. The addition that is used in stochastic computation is called a scaled computation, scaled addition, and it is given by y is equal to as plus b into 1 minus s, which is nothing but a multiplexer. So this is how the DNN architecture is now completely, I mean, visualized. So it is computed using the integral stochastic neuron. So here we have the visible input layers and the processing layers are all hidden neurons. We'll have output layer given to an OR gate to get the
It's
output.
currently 1500
So
hours.
any normal neuron will take the inputs as each input xn is multiplied with the weight, and all the weights are added. So it is nothing but a weighted sum, multiply and accumulate to give the final output. So this is how a normal neuron works. So now, based on this, we have taken some inputs, and these are all these inputs 0001 and is given to the weights 0001, 0010, and we have computed the output, and we have obtained the output as 1010. So the same output is obtained here. 1010 is obtained. So that is simulated using a normal neuron. The same thing now we implemented using stochastic neuron. So initially, the input is given to each of the multiplier unit through delay elements, and the stochastic multiplication and stochastic addition is done to get an output of 1010 for the same inputs with the same weights. So this is how the stochastic computation results, and the same. So each neuron in the DBN neural network is replaced by the stochastic neuron, and the output for the DBN network is calculated. So this is how the RTL view of a normal regular neuron looks like. So with the same, the stochastic neuron is implemented with three visible nodes and three hidden nodes to get three output nodes. So this is the RTL of the DBN neural network that we have implemented using stochastic neurons. So we are able to reduce the overall delay and the path delay also. And of course, the number of gate counts is reduced, but at the cost of increasing the number of slices and the number of lookup tables. So as we can see, the number of LUTs and slices have increased, but the number of gates have been reduced. So I can say that just to implement a 4-bit neural network architecture, so we have consumed around 1600 gates or 800 gates, and we have used around what you call 16,195 gates, 15 slices, and 16 LUTs, and 48 LUTs, 69 slices, and 774 gates for the implementation of a simple. Sorry. So, just a simple. Am I? Is my screen visible?
No, madam.
Now, now is it visible?
Yes,
Yes,
madam.
ma'am.
Okay. So now let us see. So applications like this, FPGAs are not suitable. That's what we have proven. So what should we do for these domain-specific applications? For these application-specific applications, so we have to use dedicated memories, which are which has which should have a hardware controlled multi-level cache for performing the domain specific software controlled scratchpad. And in you have to make use of more arithmetic units, or you have to increase the memory. So that is one guideline that we have to follow, and we have to increase the parallelism. And as far as possible, we'll try to reduce the data size by considering quantization instead of considering 32 or 64-bit integer or floating point value. Go to a domain specific 8 or 16-bit integer or floating point value, and just not use any programming language. Go for domain specific language like Python programming or Verilog programming, like that. So those are the important guidelines that we have to follow. So the most promising processors that are popular among the researchers who are implementing the VLSI architectures for deep learning are the tensor processing unit, the catapult processor, the crust processor, and pixel visual core processor. These are the four most important or popular processors among the research community to implement these deep learning architectures for either computer vision applications or speech processing applications. So you can see the memory size 24 million bits, 4 million bit accumulators, 65,536 max, and but easy parallelism is there, but the smaller data size, they are considering only 18-bit, 8-bit, and 16-bit integers. And of course, the crust is using a little bit bigger data size with 21-bit floating point operations. And each of them are using a domain specific language. For example, the tensor processing unit is following the tensor flow, and catapult is using totally Verilog. Except catapult, all of them are using TensorFlow. So this is how we have to think when we are implementing deep learning architectures. So if the design target, we should for the design target we should allocate dedicated memory. The architecture should have a larger arithmetic unit, and we should consider parallelism. We should consider small data size, and we should use domain specific language. So these are the important guidelines for implementation of domain specific algorithms and deep learning architectures. So let us learn about in brief about process for implementation of VLSI architectures for deep learning, starting with the tensor processing unit. Google has developed this tensor processing unit, which is an application specific integrated circuit. So this first TPU was brought forward in 2015, and the latest one is brought forward in 2018. And the heart of this tensor processing unit is a 256 by 256 8-bit matrix multiply add. It's just not matrix multiplication. It is matrix MAC, multiply and additional unit is there for this tensor processing unit. So it's just not a processor, but it is the co-processor on the PCL bus, extended PCL bus. So this is the architecture for the tensor processing unit. So the IOs are connected to this PCL bus. The IOs are connected through the PCL bus, and the rest of the operations are connected through normal bus architecture. And it has a, 2133 DDR3. And you see here, the most important one here is the matrix multiply unit. So this matrix multiply unit should multiply the inputs and also the weights. So the weights are fetched by FIFO from the DDR3, and the multiplications are performed by making use of systolic multiplication, and the nonlinear activation is calculated using this activation register here, and the normalization or pooling is done by means of this unified buffer local architecture, and the instruction set is having, this is the instruction set that can be fetched to perform these operations. uh, so the TPU, the tensor processing unit is not a RISC processor; it is a CISC processor, and this TPU is not having any program counter. It doesn't have any branch instructions. There are about 12 instructions for this TPU, and five are the most important ones. One, the read the data. Second one is to read the weight. Third one is to perform matrix multiplication and convolving operations. And the fourth one is to perform the non-linear activation function, and to write the output in a host memory. So these are the five important operations that are performed by a tensor processing unit. So as I told you, the multiplications are done by making use of a systolic array, and so this is the CPU that was developed by what you call Google, so which is less than half of the size of the Intel Haswell CPU. So this is fabricated using 28 nanometer process with 700 megahertz clock. So this is a tensor processing unit developed by Google. And so as following that guidelines for any domain specific application, this is using 24 million bits dedicated buffer, and 60% of the memory, and 250 times the arithmetic units, 250 times the arithmetic units of the classic server CPU. And it has a two-dimensional SIMD parallelism because of the usage of systolic array, and it just uses 8-bit integers, because of which the reduction of data size is possible, and it uses TensorFlow as a domain-specific programming language. So now we have the processors for implementation of VLSI architectures using Microsoft Catapult. Catapult is brought forward by Microsoft. So in the TPU was using an ARM processor, whereas this Catapult is using an FPGA PCLE board with 32 million bits flash memory, and it has two DDRs. And the programming, because it is using an FPGA, the programming is done using Verilog RTL, and but the shell size is 23% of the shell size of the FPGA. And this is the detailed architecture of the Catapult. And so the guidelines, how the Catapult is following the guidelines of DSA is it uses 5 million bits dedicated memory with 3296 ALUs, and parallelism is obtained for 2D SIMD for CNN and MISD parallelism for search scoring. And it uses a mixture of 8-bit and 64-bit floating point to reduce the data size. And as I told you, Verilog, it uses Verilog RTL for implementation. And then Intel has developed one more processor called Crest for training the DNN with 16-bit fixed point and uses a 32 by 32 matrix multiplication. It has combination. The memory is a combination of SRAM and high bandwidth memories. It has two high bandwidth memory banks, and one more architecture for implementation of visual core is brought by this architecture is brought by Pixel with the name Pixel Visual Core. So it has a image processing unit and can perform the convolution operation. And mainly so it has the input is taken from the lens through line buffers, and convolution operations are performed using two-dimensional kernels, and the output is stored in a DRAM. So this is how it works. So the dedicated memory is 128 plus 64 million bit dedicated memory per core, performs 16 by 16 two-dimensional array of processing elements, and the parallelism is achieved by two-dimensional SIMD and very large instruction world. And it is the data size is reduced by using a combination of 8-bit and 16-bit integers, and it specifically uses halide for image processing and TensorFlow for CNNs. Everything is fine so far, so good. We have talked about how a dedicated processor is important, how we can perform any deep learning architectures using the deep learning processors. But the major problems that are associated with this kind of implementation of VLSI architectures is mm, that it costs around 100 millions dollars to design a custom chip, and we the performance was not calculated before. It was added as an add-on, and uh, it is difficult to choose right DNN task for a given hardware, and the number of inferences per second is just for that. It is a fair summary performance metric. These are some of the fallacies and pitfalls. So even today, today actually not. I don't say today. Even today, the most promising or the most challenging, uh, I mean. Task that is faced by the research community in the area of VLSI is to develop a processor that will be suitable for performing the deep neural network architecture. If not a processor, even a co-processor is also sufficient, which can be not only, I mean, like reducing the data size, but can we consider memory optimization also is one of the most promising research problem we can address to explore the research in developing deep learning architectures for VLSI. So I thank the organizers for giving me an opportunity to deliver a talk on the VLSI architectures for deep learning. So with this, I'm open for any queries that can come.